push it for like a month. But I'm gonna try and rent my apartment starting like March or April. Because the housing in my area is like crazy. Like right before 4th of July weekend, it freaks out.
Okay, so I didn't
Try and rent a place and just like, oh.
Yeah.
Yeah.
Yeah, and then it'll be up front.
Alright, good afternoon. So, we missed two lectures, so I'm gonna have a quick refresh on what we covered, then we continue on plane stress transformation, and hopefully on Wednesday I'm gonna start covering more circle. So, what we learned so far, we talked about the stress definition. So we learned if we have a bar like this, if it's under axial load of the P, and we are interested about the stress at point A, it's an incomplete statement if we say the stress at point A is equals to whatever, unless we specify the plane passing through that point. So I can pass infinite plane through point A. So first I should specify the plane, then I can define the stress at point A. So we learned we learned that for something like this, passing a plane with the angle of theta or phi, we could find the projection of this force in tangential and perpendicular direction. So P N and PS. PS is making the shear stress and Pn is making the normal stress. So the sigma, which is going to be Pn dividing by the area, is going to be P dividing by A times cosine square of theta. And shear stress is going to be Px sine to theta, P over 2a times sine up to theta. So depending on the different value of the theta, we are going to have different value for the normal stress and the shear stress. And the extreme value for normal stress at theta equals to 0, and 90 degree, we have extreme, sigma max is going to be P over A, sigma mean is going to be 0. And the extreme value for this is going to be theta equals to 45 and theta equals to 135. Tau max is going to be sine of 90 is going to be 1, P over 2A, and tau mean is going to be negative P over 2A. So at the different angles, we are going to have different normal and shear stress. Then we introduce the state of stress elements for point A, for a general point like this. So you can imagine a cube which has 6 faces, or 6 planes, 1, 2, 1 on the back, 3, 4, 5, and on the left side we have 6. And in each plane we are going to have 3 terms of the stress, 1 normal and 2 tangent stress elements. So totally you can imagine 9 terms. One, 2, 3, 4, 5, 6, 7, 8, 9. Each plane has 3 terms. There are 3 planes we are gonna have 2 times 3, 9 terms. And then we learned that xy, tau xy is gonna be equal to tau yx, tau xz is gonna be equal to tau zx, and tau yz is gonna be equal to tau zy. So it's gonna reduce the number of stress terms to 6. Which is a general state of stress for a point. Then we talked about the plane stress. What if all stress elements in one plane are 0? It can be this plane, or plane Z. So I assume plane Z is the plane that I would like to have all terms equals to 0. So sigma. So plane stress means all terms of the stress in one plane, it's gonna be 0. So sigma Z equals to tau Zx equals to tau Zy is gonna be 0. So if all stress elements in this plane are 0, I'm gonna have only sigma x here, tau xy, tau yz is gonna be 0 because of this. Here I'm gonna have sigma y, tau yx, and tau yz is gonna be 0. No stress elements here. On the opposite plane, I'm gonna have just the reaction of the stresses. So something like this. Now, if you have look at this cube from front side, you are gonna see just one square, just this square, with no stress applied to that. You don't see anything on this square, but from the side you will see sigma x, which is this, tau xy, which is this, sigma y, tau yx or xy, they are the same. I'm just using the same subscription for this. Sigma x, sorry, tau yx or xy. And it's gonna look like this. So this one is gonna represent the plane stress, but we know that the cube is gonna be the state of stress when we have a plane stress. Now we would like, on last Monday class, we would like to know how the stress terms, how sigma x, sigma y, tau xy are changing if I pick the different plane. So if I change the plane, so for example, if this is my plane, if I pick this plane, I'm gonna have something like this, if this angle is phi. If here I have sigma x and tau xy, sigma y, and tau xy, what would be the new sigma and the shear stress on the new plane? That's a question that we tried to derive on last Monday class. So we would like to find two expressions like this. Sigma and shear stress as a function of angle of phi and the other terms of the stress that we have here. What we need to do for this one, for this part that we have, we should write the summation of the force equals to 0 in x and y direction. If we do that, we can derive two equations, one for sigma and one equation for shear stress. So I'm gonna write the final answer here because I derived for sigma on Monday class, but the shear stress is gonna be the same. Just to save the time, I'm gonna write the final expression. So the sigma is gonna look like this. This normal stress on this plane is gonna be this term plus sigma x, sigma y, and tau xy are given. We know what would be these terms. If we pick different plane with the angle of phi, what would be the value of the normal stress on the new plane? It's gonna be this equation. So it's a function of phi. You change the phi, you will get the value of sigma corresponding to that angle. And that angle representing the plane that we are talking about. So, and the sigma is gonna be negative of this sine of 2 phi plus tau xy cosine of 2 phi. So just plugging the angles, whatever is the plane, then find the sigma and the tau corresponding to that. We call these two equations plane stress transformation equation. So these two called plane stress transformation equations. Two equations, one for the normal, one for the shear stress. They are representing the normal stress and the shear stress on the new plane. They are a function of phi. Any question before we do the class activity? All right, here I asked you at which angle should I cut or should I pick the plane such that I would like to have the maximum normal stress. That was simple. You just look at this, say, all right, cosine of theta, cosine square of theta is gonna have the greatest value when theta goes to 0. So if I pick theta such that cosine square of theta is 1, I will get the maximum value. So what would be that angle is going to be theta equals to 0. And the minimum value of the cosine square is, it occurs at 90 degrees. When cosine square is going to be 0. So that was easy. But here, if I ask you at which angle the maximum, I'm going to have the maximum normal stress. I'm looking for extreme value of the sigma. What would be the answer? So find me the angle of phi in which sigma is going to be in extreme values. Is that clear what I'm asking for? Just think about any function of y as a function of x. At which value of x I'm going to get the maximum y. you know what you need to do. So do the same thing for sigma. Right.
Yes, yeah.
All right. Number 7. Nice. Where should we start? I mean, I'm not necessarily.
What do you want to differentiate
Sigma with respect to.
sigma?
Okay, exactly. We should different here. If I ask you what would be the extreme value for the x, you are going to differentiate y with respect to x. It's going to be 2x plus 3, and then set it equals to 0. We are doing the same thing. I'm asking at which value of the phi I'm going to get the extreme value for the sigma. So d sigma over d phi, set it equals to 0. It doesn't have any phi, so I don't differentiate that. We know that derivative of cosine of 2 phi with respect to phi, it's going to be negative 2 sine of 2 phi. Negative 2 sine of 2 phi. And derivative of sine of 2 phi with respect to phi, it's going to be 2 times cosine of 2 phi. So the second term has cosine of 2 phi. This is a coefficient, is not a function of phi. So derivative of cosine of 2 phi with respect to phi is going to be negative 2 times sigma x minus sigma y divided by 2 sine of 2 phi plus third term. This is a coefficient, is not varying with phi. So I differentiate sine of 2 phi with respect to phi. It's going to be 2 cosine of 2 phi. Set it equals to 0. I can cancel out these 2. It tells me negative sigma x minus sigma y dividing by 2 times sine of 2 phi plus tau xy cosine of 2 phi equals to 0. this is negative, I move to the left side. I'm gonna get tau xy cosine of 2 phi equals to positive sigma x minus sigma y dividing by 2 sine of 2 phi. I divide both sides by cosine, I will get tau xy equals to sigma x minus sigma y divided by 2 times sine of 2 phi divided by cosine of 2 phi. I just divided by cosine of 2 phi. And this is going to be the tangent of 2 phi. The tangent of 2 phi is going to be tau xy dividing by sigma x minus sigma y divided by 2. So any angle which has this tangent of 2 phi, it's gonna give me the extreme value for sigma. Why? Because I set the derivative of sigma with respect to phi equals to 0. I solve for that angle and I got this equation. Any question about this? Just the process or the steps that we did? Just quick example. Suppose it's sigma x is 60 megapascal. Sigma y is positive 30 megapascal, and tau xy is 15 megapascal. So look at the plane stress. Sigma x is 60, tau xy is 15, sigma y is 30. We would like to know for this stress element which plane is going to give us the extreme value for normal stress. At which angle should I cut, or should I pick the plane such that the normal stress is at extreme value? So the angle is going to be the tangent of 2 phi is going to be 2 tau xy 15 sigma x 60 minus 30 dividing by 2 sigma x minus sigma y divided by 2, and tau xy is up there. 60 minus 30 is going to be 30, dividing by 2 is going to be 15. 15 over 15 is going to be 1. Which angle has the tangent equals to 1? It's going to be either 45 degree, 2 phi, the tangent of 45 is 1, or 180 plus 45, 225. These two angles, they give us tangent equals to 1. So I divide by 2. Phi 1 is going to be 22.5. Phi 2 is going to be 112.5. So if I cut it at the angle of 22.5, I will get the extreme value of sigma. The other extreme value is going to be 112.5. One of them is corresponding to the maximum normal, the other one corresponding to the minimum. So one angle corresponding to the max, the other one corresponding to the mean. But both are extreme value for normal stress. Is that clear? Alright. So we call this angle's principal direction. I use the index of P, which represent
Dr. Gabby,
yes,
is that P2 or P2?
2 phi 1 and 2 phi 2. Yes. I just want to show you that this one has two answers.
Yeah.
So this 22.5 and this one 12.5, we call them principal direction. So the definition of the principal direction means the angle or the plane at which we have extreme value for normal stress. So these are phi 1 and phi 2 in this example, which are 22.5 and 112.5. So now the question would be, what would be the value of the normal stress at this principal direction? Here, I'm looking for this. What would be the sigma max and sigma min at principal direction? What you need to do, you just need to plug in this angle in this equation. You have the angle is 22.5 in this example, and 112.5 for the other principal direction. Just plug in 22.5 here, find the normal stress. For the other extreme, just plug in 112.5 and find the normal stress corresponding to that principal direction. But I would like to get an expression for that, so I'm going to do this right here. Let me start by plugging in this equation. What would be the shear stress? What would be the shear stress if we have principal direction? I'm looking for shear stress at phi p. Look at this equation. The tangent of 2 phi p is going to be this, or right here. Tau xy cosine of 2 phi is going to be equals to this. So in this equation, tau is going to be, let me have this negative sigma x minus sigma y divided by 2 sine of 2 phi p plus, just look at the second term, tau xy cosine of 2 phi p. Tau xy cosine of 2 phi p is going to be this equation. So I substitute this. I substitute this by this one. So it's going to be plus sigma x minus sigma y divided by 2 sine of 2 phi p. This is negative, this is positive. This coefficient equals to this coefficient, and we have sine of 2 phi p. It's going to be 0. So at the principal direction, shear stress at principal directions are always 0. I just plugged in the phi p in this equation, I got the shear stress. Here also you can check. This is the principal direction, just theta equals to 0. What would be the sine of 0? It's going to be 0. So the shear stress at this direction is going to be 0. the other extreme was 90. What would be the sine of 180? It's 0. You will get shear stress equals to 0. So shear stress says at principal direction are always 0, and the equation is going to show this as well. I just need to find the sigma at principal direction. It needs just some mathematical steps, and I love to show that, but to save the time, I just explain the steps and write the final result. What you need to do first, you substitute sine of 2 phi. Look at this. At principal direction, what would be sine of 2 phi? Sine of 2 phi would be this term divided by this coefficient. Tau xy cosine of 2 phi divided by sigma x minus sigma y divided by 2. What I did, I just divide this by this one. So this divided by this is going to be sine of 2 phi. So on sigma equation, just substitute sine of 2 phi by this one. So it's going to be sigma equals to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine of 2 phi plus tau xy sine of 2 phi. We are going to have this tau xy divided by sigma x minus sigma y divided by 2 cosine of 2 phi. So this times this is going to be a square. We still have cosine of 2 phi. It's going to be principal. If you remember, or you can do simple calculation, 1 plus cosine square of angle of x is going to be 1 over 1 plus the tangent square of x. Cosine square of any angle is going to be 1 over 1 plus tangent square of that angle. We can easily show it that. What I'm going to do that, I'm going to change x to 2 phi. And say cosine square of 2 phi is going to be 1 over 1 plus tangent square of 2 phi. And then I square root, I say cosine of 2 phi is going to be positive and negative 1 plus square root of tangent square of 2 phi. Just do the square root. And positive and negative both are valid because we are doing the square root here. What would be the tangent of 2 phi phi? We know the value of that. Just plug in here and replace cosine of 2 phi phi with that new expression. What we will get at the end, it's gonna be this. Sigma, it's going to be sigma x plus sigma y divided by 2, this term, plus and minus. One is corresponding to one principal direction because we are going to have two principal directions. The other one is corresponding to the second. Sigma x minus sigma y divided by 2 squared plus tau xy squared. So if you follow the steps that I explained, you will get this value for a normal stress. If I ask you what would be the shear stress, you can say it's going to be 0. as I showed here, the shear stress is gonna be 0. We will get two values for the normal stresses, two extreme values. One is gonna be maximum and corresponding to one principal direction. The other one is gonna be the minimum value, which corresponding to the other principal direction. How can we get two? Because here we have positive and negative, plus and minus sign. We call this value principal normal stresses. The value of the normal stress at principal direction at P is called principal normal stresses. So one and two, principal normal stress. Again, what will be the principal normal stresses? They are normal stresses corresponding to phi p. And what is the phi p? Phi p is the principal directions. What are the principal directions? They are the angles in which we will get the extreme value for the sigma, which can be shown here. So, plane stress transformation and more secrets, they have many details. So make sure that you are following the steps, and if you confused, just ask me before I go forward. Question? Any question on this? All right. This is very important things. The original state of stress is a cube, but it doesn't have any terms of the stress on display, so we can represent it with a square. So on this plane stress, we could figure out what would be the principal direction and what would be the principal normal stresses on this square or on this one, on this cube. But we should remember that we have the third plane, which is sigma plane of z in this case. And on this plane, we have shear stress equals to 0. Since shear stress are equals to 0, the normal stresses on that plane, which again it's going to be 0, it's going to be the principal normal stresses because it's a definition of the principal normal stresses. What would be the principal normal stresses? They are the normal stresses where shear stresses on those planes are 0. So this plane also has this specification. All shear stresses are 0. So the number 3 principal normal stresses are, it's always equals to 0. So sigma prime 3 is gonna be 0. So we have 3 principal normal stresses. 2 coming from this equation, and 1 is gonna be always 0. And we are talking about the plane stress elements. I'm gonna use this shortly, maybe at the beginning of the Wednesday class. Any question before we move to the shear stress? Good? All right. So we are going to do the same things with this one. At which angle? At which angle I'm going to get the extreme value for the shear stress? What I need to do, I cannot, it's not clear which angle it's going to be. I'm going to differentiate that with respect to phi. Just to save the time, I'm skipping some class activities. You were supposed to do it by yourself, but I'm gonna drive it by myself just to save the time. But the process is gonna be the same. I'm gonna differentiate shear stress with respect to phi. So let me. Derivative of shear stress with respect to phi. This is the equation. The derivative of sine of 2 phi I have over there. It's going to be positive 2 cosine of 2 phi. 2 times negative sigma x minus sigma y divided by 2 cosine of 2 phi plus derivative of cosine of 2 phi is going to be negative. Negative 2 times tau xy sine of 2 phi. If I'm looking for extreme value, I should set it equals to 0. I'm looking for this angle. At which angle I'm getting max extreme value for the shear. So I can cancel out these two. I'll keep this in one side and move the other to the other side. Negative sigma x minus sigma y dividing by 2 cosine of 2 phi equals to this negative. If you move it to the right side, it's going to be positive. Positive tau xy sine of 2 phi. I divide both sides by cosine of 2 phi. I will get negative sigma x minus sigma y dividing by 2. Cosine of 2 phi dividing by cosine of 2 phi is 1. Tau xy sine of 2 phi over cosine of 2. Sine divided by cosine is going to be the tangent. So the tangent of 2 phi, I use the letter of S to represent the shear. The extreme value for the shear. It's going to be the tangent of 2 phi S. It's going to be this dividing by this. Negative negative sigma x minus sigma y dividing by 2 divided by tau xy. So this angle is representing the shear stress, the angle in which I will get the extreme value of the shear stress. Same thing that I did for principal direction. What would be the value of normal stress at principal shear stress direction? I'm looking for sigma at S. Sigma at principal shear stress direction. Equals to what I need to do, I need to plug in phi s here in this equation. It's going to be sigma x plus sigma y dividing by 2 plus first term sigma x minus sigma y times 2 cosine of 2 phi. Let me keep that for now. Plus sigma x minus sigma y cosine of 2 phi s plus tau xy sine of 2 phi. Look at this. Tau xy sine of 2 phi, it's equals to negative of this term. I just change this to negative sigma x minus sigma y divided by 2 cosine of 2 phi. This term is exactly opposite of this term. So I can cancel out these two. It's going to be sigma x plus sigma y divided by 2. So the value of the normal stress at the principal shear stress direction is going to be sigma x plus sigma y divided by 2. What would be the shear stress? The same thing that I did for principal normal direction. If I do that, I will get the extreme value So if I plug in sine of 2 phi and cosine of 2 phi by phi s, which are the shear stress, principal shear stress direction, I will get this value for the shear, which are the extreme value. I don't want to say maximum because you will see shortly that the maximum term is, we should be careful to use the maximum term for this equation. It's a extreme values. And the normal stresses at that point, at that direction is going to be this. Compare principal normal direction with the principal shear stress direction. At principal normal stress direction, the shear stress is always 0. Shear stress equals to 0, we get the normal stresses for sigma. Here, at principal shear stress direction, we have value for the sigma, it's not 0, and we get the value for shear stress term as well. Any question on this? Again, plane stress transformation equation and the more circuit, they do have many details. So I try to be straightforward when I explain, but if it's confusing, just it's time to ask. On Wednesday, I summarized these two principal shear stress direction and principal normal stress direction in one table with the angle of principal directions for the normal and the shear and the terms corresponding to that. No homework for this Thursday. Yes.
If we wanted to review this stuff, is this stuff in our current textbook, or should we go back to our?
You can find these things on the textbook. Also,